It was fantastic. All right, so this lab, if you plot the data on a graph, you should end up something like this. Which, tell your partner which color represented the products and which was the reactants. All right, that's good. And this is concentration. Well, it would be height technically. For the lab, it was height, but it's concentration essentially versus time. All right, if I were to put a circle on here to show when equilibrium was not, where would I put it? All right, about right there. I don't know how the circle tool works very well, but whatever, that part. Okay, it's definitely not where the cross is. We don't care about that point at all. This chapter, we will worry about where the lines go parallel or the slope goes to 0. So this is what it looks like on a graph. We kind of talked about it in the lab. Equilibrium happens when the forward rate and the reverse rate are equal. Now I'm going to blow through notes, and I'm not going to wait every slide for you to write something down. I did put this stuff finally this morning on Canvas. If you want this PowerPoint, you can open it up on your devices. And it's always a little different than what you see, because this is like the one I write on, not the actual PDF. But anyway, it's close enough. Okay, so here we go. The concept of equilibrium. The next 3 chapters are on equilibrium. It's really important. It is guaranteed that it will be 20% of the overall exam. What? It's on electrochemistry. 20% of the AP test is from equilibrium. It's most likely from the next unit, chapter 16. Well, actually, sorry, 15 and 16 are together. It's chapter 17 is most likely where, I'm just lying. It's the end of 16 and the start of 17. I'll just stop talking. Okay, here we go. Equilibrium is the idea that we make a bunch of stuff, but then we make so much of it that some of it breaks apart, and we eventually come with a rate that goes that way and this way at the same speed. We know that a rate of a reaction is dependent on concentration of the things. Over time, the concentration of the reactants decreases. The concentration of the products increases until eventually the rates become equal. All right, does that mean you have equal amounts of A and B? No, it means you're exchanging the same amount of A and B. So it's essentially like I make money for my job and I spend money. And at the end of each month, hopefully I'm at least positive or not negative. I roughly spend about the same amount I make. Usually when you get a raise, you start to spend more until you reestablish a new equilibrium position. If you get a pay cut, you'll spend less. All right, so it's pretty similar.
How would you ensure that if you want a certain substance, how would you ensure that that's what save that substance?
You can manipulate the conditions. We'll learn at the very end about what's called the Chatelier's principle, which is an application of that idea. All right, TA, will you plug my iPads in? They're getting pretty low. Okay, next up. So equilibrium with the same rate, forward and reverse, but not when they have the same amounts. Okay, this is just going to say we already said, but as the system approaches equilibrium, both the forward and reverse reactions are occurring at equilibrium. The forward and reverse reactions are proceeding at the same rate. So this, you'll see this graph once in a while. It's the rate versus time, and they always come to be equal to each other. But this graph is not as common as this graph, which is concentration or pressure versus time. So that's what this is. Once equilibrium is achieved, the amount of each reactant and product remains constant. Now, this chapter very quickly will jump into math. The math it's not that bad as long as you learn it. But don't don't let the math confuse you. What the math is really doing, it's just comparing essentially what this concentration is to what this concentration is at equilibrium. It's a ratio of my products to my reactants. All right, so I mean, the math will get a little confusing, but ultimately, just think about it. It's just comparing where the two lines are to each other to come up with what we call an equilibrium constant. Now, I got to be careful. This will come up, but I'm going to say it right now. K from chapter 14 has nothing to do with K from chapter 15. Now, I know it's dumb. We're going to learn a lot of Ks. We're going to learn a lot of them. Chapter 14 is the rate constant. Chapter 15, it's the equilibrium constant. Now, the equilibrium, it definitely has to do with the rate, but the Ks have absolutely nothing to do with each other, pretty much. Okay, so that gets a little confusing. All right. In a system at equilibrium, both the forward and reverse reactions are being carried out as well. So we write this as a double arrow. So whatever, instead of H2 plus O2 making water, we now can have it go both directions. You'll see it in both styles where it's a half on top, half on bottom, or just a double-headed arrow. Both are fine. This is not technically a combustion reaction because this isn't a hydrocarbon. If this says C3H8 plus O2, then yes. But water definitely does exist in equilibrium, but it's not. If you're really going to watch or write it, you would write it as H plus OH minus goes to HOH. That's the real way they would do it. Because if it H2, this is, you don't need to know, but then you end up with a heterogeneous equilibria and it's messed up. So technically, yeah, I should have written it that way. Okay, but just know they can go both directions. All right, so here we go. The equilibrium constant. Don't stress about the P part yet. Why would I even throw that in there? We're going to learn about all these things. K concentration, K pressure, K solubility product, K acid, K base, KW. Here's the good news. They are all the same. That period should have been right there, whatever. Now, why they have a different name is because it helps us realize what we're comparing. So when it says K for concentration, that's really called Kc. And I would be comparing the concentration of my products in ratio to the concentration of my reactants. K for pressure would be Kp. Ignore these for right now. Kp, you would just have the pressure of your products divided by the pressure of your reactants. And it's kind of dumb, and I'll do it wrong a lot. Brackets mean Kc, parentheses mean Kp. Ksp, that's a specific measurement of K, or a constant, where we compare the products of something dissolving. And we do it for acids, we do it for bases, we can do it for water. They're all the same thing. Now this, I don't know why I would have thrown this in whenever I did, but P, every single one of these also has a P, pKa, pKb, I can't even talk, pKc. It all has them, and P just means we take the negative log. So you've heard of pH. That tells me how acidic something is. P means the negative log. H means H plus goes right here. So, but that's not necessary right now, but that's just in case you wonder. Okay, these two are on chapter 15. These are on chapter 16 and whatever. They're pretty not that bad, I promise. Now, don't write anything down for the next few slides. This is just kind of how we get to this idea. All right, when we have a reaction here, it goes this way. The rate law is Kf. It's like the rate constant for forward. F means forward of this concentration. for the reverse, this is a lower subscript R. We have this rate law because we're going this direction. Now, just don't worry about it. Therefore, if at equilibrium the rates are the same, we know that we can make an equal sign and we can compare these. And we end up with the K forward and the K reverse becoming this equation. Now, it came from here because we know that they're equal. And so if we want, we can solve for the KF and KR and just don't worry about that yet still. So therefore, the ratio of the rate constants is a constant at that temperature, and the expression becomes, so the KEQ here is just what we call KF over KR. You don't have to know that. But KEQ is where we take these concentrations and raise them to their coefficients, and those are the products, and divide it by the concentration of the reactants. So KEQ, I don't know why it looks like this, is equal to the concentration of products divided by the concentration of reactants. And that is all. Now, it is temperature dependent. Every one of these problems, it will tell you what temperature it's happening at. You don't ever have to use that temperature. It's just telling you that that is the temperature that it's happening.
So that's one way to basically react to it.
Yep, you definitely could. All right. So KEQ, that means the equilibrium expression or the equilibrium constant is products divided by reactants. KC is exactly the same. It's the concentration. That's what the C stands for, because you'll see it written as both for concentration. All right. And then once again, KP, and these are the only ones we'll deal with in this chapter. That is the pressure of the products, pressure reactants. And there'll be a slide that says pressure is analogous to concentration, so we can use it the same. Might be the next two slides. There might be some Pivmer, but usually it just gives you the value. All right, so to generalize this expression, the equilibrium expression for a reaction will be written the following way. So we have KEQ or KC or KP, whatever one it asks for, is equal to the concentration of your products raised to their coefficient times each other, so the product of them, divided by the product of the compound of A raised to its coefficient and so forth. Now, it's kind of annoying, but there's a whole nother name for this thing. And it's not used very often, but it's been used before on the test. And that is this term right here. I don't really know its root, but KEQ is also called the mass action expression. And my first year or two, I didn't really teach kids that. And then a kid, he came the day after the AP test and he said, I failed that. I don't know what a mass action expression is. I was like, we did that 200 times, but I always called it K. It's the same exact thing. Okay, so it's pretty simple. It's P over A, or R, sorry, P over R, and you just raise them to their coefficients. So if I go right here, just a couple of examples. Now, most of these as written are not reversible. I just cut these from a normal chemistry lab book. They're not like they would really be one, but we just grabbed it anyway. Okay, so the first thing, we go back and we have to be able to balance equations. Okay. All right. So number one is 2, 4, 3. So now just pretend that this one would work. So we put KEQ would be equal to the concentration of aluminum raised to what? The fourth. And the concentration of O2 raised to the third, divided by the concentration of Al2O3 to the second. This would be my mass action, or KEQ or my KC for the reaction in number 1. Does that make sense? All right. Well, even the kid in the hall says it's great. All right. Well, hello. I'm assuming you're using me for my keys.
Yeah, we're wondering if we can use the track flags to mark.
All right, so I was lazy. I almost didn't hit record. MgNO3 to the first, H2 to the first, Mg to the first, and nitric acid to the second.
All based off of the balance.
Uh-huh. If you can't balance it, you're in trouble. Okay, now, because pressure is proportional to concentration for gases in a closed system, the equilibrium expression can also be written as P. So that just means, like, it looks weird, but it's the pressure of C raised to the C. This is ugly. This is really annoying. Whatever. You with me? You just take the ATMs and add them, or put them in here and raise them to their exponents. That C should be on the outside. It's fairly simple. You take the ATMs it gives you, or you calculate them, and you plug them in. And we get K pretty quickly. Oh, it's exactly the same thing. You're just given ATMs instead of molarity. All right. So, are you serious? I hate molality because we don't usually measure things out in mass. We measure them out in volumes. So,
It's less accurate.
I'm sorry. Well, I'm not going to say I'm sorry because no one needs to apologize, but I don't know. That's just how it rolls. Okay, so now let's apply. What is KC? I didn't put whether these were whatever. I can put a capital M and then we're ready to roll. So, yeah, it is. Well, how cool is that? So I just plug things in. KC would be equal to AG2S to the first, right? Over AG squared and S to the first. You with me? I took my products and raised it to the exponent, divided it by my reactant, raised to its exponent. And I had to do both. So then I just plug it in. KC will be equal to 0.02 divided by, then the AG is 0.02, but I square it this time, times S, which is 0.01, and I'm ready to roll. Do you understand where I put everything in? Okay, what did I get? 5,000? Okay. Yep. C means concentration, yes. What?
How did you end up with less moles
What do you mean less moles?
on AG2S?
Okay, there's no rule on the planet that's called the law of conservation of moles. It would be matter. We'd end up with the same mass, I promise, but there will be an increase or decrease in moles all the time. Okay, my friends, KC or any K, I was going to say a K can be big or small. Don't freak out when your answer is 5,000 and then the next one on the test is 2.8 times 10 to the negative third. It can be whatever it feels like. Don't judge it by its size.
Whatever it wants to equalize that day.
Yeah, it will do whatever it wants. Okay, now let me tell you something, and we'll learn about it. But if it's big, that means its product dominant. And this is in the notes later. But if K is a big value, it means that there's more products than there are reactants. Now this one looks weird, but just go with me. All right. If it's small, that means there's more reactant at equilibrium or reactant dominant. Oh, that's to be,
Small is less than one.
yeah.
Since K is a constant, it shouldn't have a unit, right?
This does not have a unit. It's a unitless value. All right, now we'll talk more about this, but don't, it's just, some of them will be on the test, like, I got 25,000, I knew that was wrong because it's too big. That's false. That's, it can be any value, especially since I make numbers up. And the way this test is, it's one of those where I change the variables. So Nisha could get 20 and you could get 20,000 and you're both right. Yeah, it'll be like that.
I like that because then I can.
Okay.
This
All
is
right.
why I think it's 100% on the test.
Well, the problem, one time he got 100% and the person next to him, no names, got like a 99.
Really? Yeah, well, it's tempting when you see like two up there. And look, this is behind me. Pretty smart individuals right out here.
Yep, you're surrounded by genius. Okay,
I'm just-
so
I'm in the back. I can't even.
one more time. This chapter, chapter 15, we deal with these three things. These are the same sort of. KEQ just means in general, any relationship product over reaction or reactants. And it's called the mass action expression. KC is specifically K just for concentration. It's also known as the mass action expression. I learned my hard ways that I need to use that term more. All right. KP, that just means K, but it's the mass action expression for pressure. And that's when it's in gases. Anyway, that's that. Can we please get the math on board? Yes. Here we go. Calculate KEQ for the above reaction if the initials were right here. Not initials, sorry, the equilibrium concentrations were right
So
there.
we want to solve for this.
Yeah, this is a math answer.
Okay. Yeah.
I know already that a lot of you will get this wrong.
Because of our balancing.
Yep. Usually it's not a day, so I'm not sure why it is a day at all. And like I said,
No bad.
hopefully you don't think this is awful. That's what it is. It's not bad, right? Now, of course, it gets worse. You're welcome. Okay, here you go. This is how all my test questions looked back in the day. Because we got a new computer and the test bank and that computer didn't really talk to each other very well. You're welcome. It is. This is an arrow.
Oh, I thought H2. I don't have to do Y.
Are we out of here 4 minutes or 14? I don't remember. Okay.
Oh, okay.
No.
It's going in order.
That's what respectively means.
What if you mix? That'd be a terrible.
Then you get it wrong. Wow, it's only 37 degrees.
I like how respected that.
Any of you guys were saying
Yeah, the sun makes it feel a lot warmer.
It looks beautiful, but ain't never been beautiful starting with a 3. If I remember right, the answer is E, but I could be wrong. It's, you're welcome, my friend. Is it E? From a year ago, coming in for the win. John is a mood sometimes. Yep, that's what I got. Nope, wait, I got D. All right. I, I don't know, but this is no bad, right?
Yeah,
So bad.
I like it.
All right. You're welcome, people.
Yeah, those ears. Wow, that's pretty.
The A, that's the broken, whatever they call that part of your nose, the bridge. You're welcome. Oh, this is like my favorite thing of the year right here. But we're done. We're out at 1, right? Why am I thinking 1? Okay, okay. Okay, yes. Okay, we're good. We're good. We're good. Ice, tables, I love them. I hope you do too. Please make sure you pay attention. A useful and useful. What is this kid? A useful tool in solving equilibrium problems is an ice chart or ice table.
Yeah, it's gonna.
It's-
Because it's like a yes sound, it's only if it sounds like a vowel.
Yeah,
Sounds like it's a vowel.
right. Grace for the win.
Yeah.
Okay, here we go. We're wasting time. I stands for the initial concentration or pressures for each species in the reaction mixture. C represents the change in the concentration or pressures for each species as the system moves forward. Do you know what I mean by species? Species means X, Y, or Z. All right. E represents the equilibrium concentrations of each species when the system is in a state of equilibrium. Okay, so these are the numbers we need to get because those go into the expression, right? But you'll typically be given only initials and then 1 either at equilibrium or 1 that has changed. So just kind of follow with me. I love these. A sample consists of 0.5 moles of X. It's placed into a system with a volume of 0.75 liters. So this is at the start. At equilibrium, the amount of X is known to be 0.35. All right, so we write out the equation. And this is how the ice table will be constructed. So you have your initial, your change, and your equilibrium. Write out your reaction, and I would definitely put the arrows. They did not. I just cut this from the online textbook and the plus sign. Because if you put the arrow over here, life can get really bad. Okay, so what it tells you here is that you started with 0.5, but you now have 0.35.
So you change.
So your change was negative, be careful, negative 0.15. Is everyone okay with that part so far?
Wait, how did you know which one was, how did you know which way was that?
Because of the equation above.
This?
Oh, okay.
Yeah, so you just write it out and then make these columns. All right, so that's negative 0.5. Now, everything else has to do with the coefficients. So this one's easy over here. Z changes how much?
Double the amount. So
Double, but it's a positive. Why is it a positive?
because you're giving more.
All right, that's true, but it's because it's a product. Reactants go down, products go up. That's why this was a negative, and it was also a negative because of the math. All right, now, this one's a little tricky. This one is 1.5 times this value. Where did I get 1.5?
Because it's
3 halves. So you take this value and multiply it by 3 halves and tell me what you get there.
0.225. And then you just add.
And that, is that a positive or a negative there?
It's
Positive.
product.
Okay, now we just do the math. 0 plus 0.225 is
0.225.
0 plus 0.3 is And then we're ready to plug it into the expression. So we take, I'm just going to write it here. We have y cubed z to the fourth. We okay with that? And that is over x squared. You with me?
Yes, because you just take the coefficient.
Because the coefficient, for every 2 of these that go away, 3 of these are formed. So you put the one you want on the top, the one you don't want on the bottom. Okay, so then you just plug it in.
I hate using these in math. 'cause
Mm,
they always look like
sorry.
twos.
Or B, because the way I had that, B was like sixes. Yeah. Large.
Oh, and I already screwed up. I just did it wrong. I looked at the wrong column.
Math is just-
Like 7.5.
And just looking at this, and you're not used to them, but the answer should be a small number. Because you have decimals that you're cubing and multiplying the decimal by a thing that you took to the fourth power, divided by a square, it definitely should be a small number.
What did you get again?
7.5 times 10 to the negative 4.
Yes.
Let me tell you something. 2 people on the test, on the problem like this, their calculator said 7.5 yada, 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 e negative 4, and they just put 7.5. Don't do yourself like that. You're so amazing, but you just look all the way to the right on your calculator. I don't know, I just wrote that from this answer. I'm just saying be careful because that person would have got 100% on the test, but they forgot the times 10 to the whatever. Okay, so an ICE chart makes it so we can be given initial stuff, and as long as we know at least one thing at equilibrium or at least one thing of change, we can solve the entire problem based on stoichiometry. All right, here we go. In the coal gasification process, carbon monoxide is converted to dioxide via the following reaction.
Is it via or via?
It doesn't matter. So your ice table, what would you put up here?
Via.
No. Are we really?
You would do, yeah, CO2, H2O.
Be careful. Don't put CO2.
Yeah, I meant.
Okay. Then it gives you 0.45.
Well, it's the equation back.
I won't ever speak again if you want to treat me like that. All right. Now, what are these 2 values? It doesn't give it to me.
You just have to solve for it.
Zero.
They're 0.
Because they're the product.
Now, super big timeout here. They are always 0 unless the problem tells you there is some already, which it will sometimes.
And wouldn't that be
But it would be in this sentence.
backwards?
No, it doesn't have to be. It just means there was stuff already in there. All right, at equilibrium, there were 0.19 mole of CO remaining. This problem's a piece of cake.
Oh, because they're all the same.
All right, so the whole thing when I said that's a piece of cake, if they're ones, they're pretty easy. You doing all right, TA? Okay. There's yardsticks in Goddard's room. Just go through the door and reach left. You'll find one.
I come up
Okay,
with both
that's
of
fair.
those from my dad. Shut up, Cooper.
I'm not actually that worried about it. Is this 28 or 0.28?
Yeah, point to it. No, so 13. Oh my God. Why do you say it like that?
I've never heard it said via. That's weird. Maybe it's because I'm from Vernal. Okay, you don't know how to do C yet, by the way. It's not hard, but you don't know yet. It's an equation that converts. No, KP and KC relate to each other with some math. Yes, sir. Where? Why are they not negative? The negative is the amount that it went down, but it's not the amount at equilibrium. I put the bottom row in. This kids get this wrong every single time, and it's so easy. They think it's going to be way hard. Like, I don't know. Well, it tells you it's 0.28. All right, it's right here, moles. So it's
Oh, and then you
0.28
just
times 18 grams per 1 mole, and you get an answer. What was the value?
1.27.
Easy money, my friends. That is over half of the chapter.